Good morning, good afternoon, good evening, everyone. We're really glad you could join us here today. I'm Eli Leland, the CTO and co-founder at Voltaic, and I'd like to welcome you to our webinar where we'll be talking with our guest, Dr. Philipp Wunderlich, on the topic of the digital battery factory. First, up front, some housekeeping notes. We do welcome and encourage participation from our audience today, so please do submit your questions through the Q&A function of your Zoom app. Note that participant chat is disabled for this webinar, so please do use the Q&A function to submit your questions and not the chat function. And now to talk about our panelists today. So our featured panelist is Dr. Philipp Wunderlich of Accenture. Philipp studied material science, batteries, and battery manufacturing at RWTH Aachen University in Germany before joining the battery consulting practice at Umlaut, which is now part of Accenture, where Philipp is a senior manager. So Philipp has a lot of depth on battery manufacturing and the IT world and how they come together. And so he was really the perfect guest for today's panel. On today's panel, Philipp is joined by my co-founder and Voltaic CEO, Tal Schulklapper. Tal has also been working on electrification technologies for over 20 years with extensive hands-on experience developing and commercializing fuel cells and grid-scale storage batteries before starting Voltaic with me in 2012. So we'll start with some material from our featured panelists, followed by a discussion and some questions from the audience at the end. And as Philipp will go through, we have a couple different topics to go through. So we'll do some slide presentation content and a discussion after each section. And then again, we'll welcome audience questions and may opportunistically bring them in throughout. So with that, I'd like to introduce and turn it over to our featured panelist, Dr. Philipp Wunderlich.
Yeah, hi from the Netherlands, and thanks guys for having me on this webinar. It's a pleasure. I mean, we've met a couple of times on the battery shows every here and then, and now doing this online with you in a webinar format is also pretty cool. Here to talk about digitalization in the battery factories. That's something I have been more and more exposed to in my role leading the battery practice at Accenture. So I'm coming from material science, coming from battery production technology, but I feel like working in the largest IT firm of the world, it's inevitable that you have to deal with IT topics also in the cell manufacturing context for me. And I want to give you some of the insights of the last couple of years, what we've seen in gigafactories all over Europe, in the US, and what's happening on the shop floor. But more starting with a more conceptual view on how digitalization is actually playing out in these facilities. I hope you can see my screen now, and I will now guide you through this presentation, which is called the Digital Battery Factory. We'll be featuring 3 segments, and the first one is going to be about why do we even need this in battery cell manufacturing? What's the benefit and the power of digitalization when we employ it? So this is for starters. If you're familiar with battery technology, you know how complex the battery is as a product. So this slide should give you this impression from the left view, which is the product perspective. The lithium-ion battery cell is not a trivial product. Some people would say it's a living organism. It's a very complex device to work with because you need to bring together classical engineering and scientific domains, chemical, mechanical, and electrical engineering, and a lot of electrochemistry if you want to understand it. And this alone gives you a lot of complexity when it comes to the product properties. There's about 50 of them. If you just take the finished good, the battery cell as a device, and then all these components in there, let it be 10 to 20, depends on how many additives and secret ingredients the cell makers put in there, all come with their subpart properties, which can add up to more than 1,000 parameters you could deal with on a product level. So requirement books for a modern battery cell for electric vehicles and storage systems can be very big, can be 300 pages, lots of specifications you find in there, and those properties change over the lifetime of the product, and that gives a lot of people a lot of headache. And to make it worse, we need to produce it. And now if we want to proceed in the energy transition and really bring batteries to the market, we need mass scale manufacturing in the gigafactories. And here we also have some challenges that we encounter given the complexity and the unique manufacturing style that you need for the batteries. So basically here we have to juggle between the continuous and discrete manufacturing. So 2 traditional manufacturing domains that are merged together. We would have roughly 10 to 20 main manufacturing steps that would bring you from the active material powders to the finished good. And then you can break this down in roughly 10 times the number of sub-process steps, because it's usually a highly automated process where you have a machine executing maybe 10 process steps in a row, could get you to 200 sub-processes. Depends on the definition of the cell maker. And then given all the machine parameters and the process parameters, you can easily go in the 4-digit realm. More than 1,000 parameters you would need to consider in a cell manufacturing plant if you were to produce a lithium-ion battery. And to make it worse, there's a lot of interdependencies between the product properties and the manufacturing style. So that's something every cell maker needs to pay special attention to. And this is something where we feel digitalization is fitting into this picture because it helps us with the complexity management. If we look at the gigafactories, so basically large capital projects aimed to build mass manufacturing of lithium-ion batteries, they are struggling with these things you find on the slide here. So that's kind of a lot of pain points that we figured from a consultancy point of view is what newcomers in the market, but also some established cell makers were facing. Of course, it's a high investment project and you need to be super competitive if you want to enter the mass market. But I think one of the key problems that we will also discuss today is dealing with the product complexity in the phase of the ramp up, which typically comes with a very high scrap rate. So you need to throw away a lot of batteries. In the batteries, it's a lot of precious material, and this hurts a lot. And basically managing this through battery quality systems could be a way out. So digitalization might help us to address some of these challenges here. And I would like to give you an insight from a study we conducted last year. This was done in collaboration of Accenture and the Fraunhofer FFB in Germany. And we checked with an industry expert survey, basically with the target audience of cell manufacturing experts and digital manufacturing experts. If we use digital technologies, how can the KPIs you see here on the left benefit from digital tools? And the outcome was, or more or less wishful thinking, that we can drastically improve the scrap rate. So that's also the desire that is expressed here by the expert, that if we use these technologies, we can improve the yield and the product quality in a manufacturing plant. On the second place, we had an increase of the uptime of the machines, or reduction in downtime and maintenance. Energy consumption, as you know, is also one of the pain points, because gigafactory can consume electricity like a small to medium-sized city. Bringing this down to optimize energy utilization, that is also very desirable. And lastly, how digital technology could affect the staff required for setting up a factory. And this is just as a teaser to create some appetite for you, how we can use these levers and actually get these benefits harvested. So what we need to bring together is basically some traditional domains, the technology view from the battery tech, which is somewhere in the interdisciplinary field between chemistry, material science, electrical engineering, mechanical engineering, but also then merge this with now experts on digital technology. Because if we are tackling this field, I would say it's fairly niche at the moment. Though the demand for a specialist is growing, you will hardly find people who have both specializations at the moment, simply because of the academic degrees you could obtain. I think there's only a few battery data scientists or engineers for modern gigafactory IT out there, and less experienced people on the market. Or these people are already working for some of the several newcomer companies we've seen in the market recently. So the message here is you need to be able to master both if you want to efficiently employ these technologies. So both battery tech and digital tech, this might give you the outcomes that we desire. How would this look in a gigafactory? But before we jump to this section, I think we have some time for discussion at this point.
Excellent. Great introduction to that topic. So yeah, a couple specific questions. So here at Voltaic, as we engage with companies that are scaling up their battery production, clearly scrap is a major issue. It's a major economical issue. It's a major environmental issue. I listen to lots of interviews with CEOs of battery companies on different podcasts. Everyone's talking about scrap. So can we go into a little bit more detail about how digital technology specifically can help mitigate scrap in battery production?
Yeah, I think this will be featured in the second and third part of the content I prepared for you today. Roughly, the idea is that jumping back to the introduction, you see all these different properties and what's not shown here, what I mentioned, the interdependencies of these properties that need to be managed. So that's just impossible for a human operator to do. And keep in mind, also given the scale of production, which is millions of cells per week coming out of a battery gigafactory of decent size, that's something that would be impossible to handle for a human alone. So we basically need digitalization, and we need to also have data analytics helping us to kind of understand the interdependencies, mapping out the properties, managing this for us. So basically our engineers can focus on more important things, for example, to fix the root causes of the quality issues. And I think this would be an interesting thing to discuss, like how do we de-bottleneck actual quality problems in production? Because the digital technologies you need to imagine as your toolbox, and the tools given to us that we can leverage to kind of improve the situation. But ultimately, it's the battery properties that would say, okay, it's a scrap cell or it's an okay cell we can sell to the market.
100%. Yeah. And I think this slide just resonates with me so much. It's one of those things I keep talking about in the battery industry. It's you have, car companies who historically employ a lot of mechanical engineers. You have just this mix of domains and expertise that you need to really understand a battery cell itself from a design principles, let alone from the manufacturing principles with, continuous and discrete processes, all these subcomponents. You're just not going to be able to figure that out or build the expertise that understands it all. And what we've seen in practice is just these two different, if you boil it down to two areas, one is it takes a long time to see if a battery cell is good or bad. You can make a battery cell and not realize it has a problem until it's in a consumer's hands. And, shortening that feedback cycle, not just in, final production, but in this ramp up phase is really the first step. And so if you could leverage the data coming off of the factory to identify early signals of what is bad in the process, whether it's with existing, formation charge and discharge data or additional sensors, if you could add some, additional measurement techniques and additional sensors to help identify these early things, that's really step one. And then that next piece, with all these interdependent sub processes and components, it is literally, almost impossible to figure out where these problems are coming from. And so that's what has led to these multi-year ramp ups of new factories, and digital technology is really going to be the only way to help, speed up that initial understanding if there's issues, and then really dialing it back to that root cause.
It sounds like we'll be diving a little bit deeper into that topic as the webinar progresses. So I'm excited for that. I wanted to ask about one other thing that was, I think, perhaps on the next slide around the impacts of digitalization. And one of them, or it was, yes, this one, with the required staff. So it sort of presents this interesting contrast where we're seeing digitalization as having the promise of reducing the required staff and thus the operating costs of a production facility. And at the same time, what we're hearing very directly and in all kinds of conversations around the battery sector is the talent gap and how there aren't enough people, aren't enough experts on, running the different pieces of equipment, the different parts of the process, how it all ties together, quality, et cetera. So I wonder if you could talk just a little bit about these sort of, potential opposing forces, one where companies are seeking to bring in as much talent as they can get, and at the same time, digitalization promises cost savings through headcount reduction. And if you have any thoughts around that.
Yeah, I think especially in Europe, we've seen how this situation has evolved over the last couple of years, given also a bit of a talent shortage on the market. And now most people who have expertise in batteries or even experience from the factories are in employment for the cell makers, traditional ones, the newcomers, and automotive companies entering this market. And all of these companies went to the market with a promise to create jobs for their region. So they have a desire to hire a lot of people, create the jobs also in the upstream supply chain. So from this perspective, it's cool to have more people on board, especially if it's the skilled people with the expertise that the market is currently drained of. And here, if you look at this slide, when we conducted the survey, I think it's important to point out we were asking for the digital technology and not the traditional hardware automation, because that would be the lever where you instinctively say, okay, if we Instead of having a manual transport of coils through the shop floor, we take an AGV or we take more robots transporting material. This is where we said, okay, we can reduce operator headcount and save payroll cost. If we just look at the digital technology, I think the score here is rather low because people are aware that by also in the first place gathering data and having this complexity added to your shop floor, you need to manage this. It might actually increase your headcount in certain cases. And also if you have the base set up that you basically obtain the production data, someone needs to manage those. The question is, will it actually save you headcount or not? It would probably shift the allocation of experts you need. And especially something that should be discussed is how many quality engineers do you need and what will they be doing? How will they leverage the digital tools they have? And will they then just focus on other stuff like the troubleshooting on the shop floor while they get all the information they need out of smart dashboards and correlations that maybe an artificial intelligence indicated to them? So it's a very tricky question, but I think overall, if I would look for a new job in the future, I think if you know both battery and IT, you will probably find.
I just think in general, just with the era of high interest rates that we have now, it's people are going to have to be much more cash efficient, and headcount is obviously one of those obvious areas. And so I don't think it's, I think there's the automation and hardware around, who's moving what between what place in the facility. But I think the other side of it really is, how much time does it take you to figure out these issues, and whether it's, reducing or eliminating a little bit of headcount. Ultimately, it's really about the ROI is really going to be around scrap rates and getting these factories productive sooner. And so that's what pays for itself. It's if you could take those factories and make more money from them, that's really the key here.
Excellent. And I must say that sort of future scenario that you painted, Philip, is especially resonant and appealing, of one of where the quality engineers are kind of getting everything that they need in dashboards, and that they can really focus on troubleshooting specific issues. That's a nice way of putting what we're trying to help our customers get to as well. So with that, Philip, I'd welcome you to introduce the next section of your content.
Okay, great. Let's move on. How to make this happen? I mean, how should we build the digital backbone of a facility? How could it look like? And the content you will see on the next slide, it's coming from a high level, and it's, I would say, a blueprint, but it's a non-binding one. Every cell maker has a different approach to it. It just should set the base for the discussion here. And of course, wording terms, everything is up for debate, but we just wanted to sort it in, help you also understand how we see it and how we could imagine the gigafactory being built up. So one of the illustrations we picked for the white paper we published is the following one, that you basically have the physical world, the shop floor with all the machines, production assets, and the cells being produced. And what we investigated is the digital space above it. And we had 3 layers that we actually picked here. The bottom one is the enabling technologies. So basically all the software platform, also operational technology you need to kind of execute and give you the functionalities you desire in the digital facility. The second layer is the digital representations or models or twins. And of course, it's a term that is heavily discussed. What's a digital twin? What is not a digital twin? But on a high level, we refer to any digital representation of these assets here, many building machines and products. And then it's getting interesting on the top layer, the use cases, so what you can do with these baseline technologies and the models, basically harnessing the benefits of the data and IT, and then enable, for example, cases like predictive maintenance or traceability in your shop floor. And that's how we built the logic of the paper. And this could look like this if you focus more on software and application view. So this slide has a lot of content on it, and would be happy to discuss how you guys see it. But that's, merging the traditional automation hierarchy on the left, going from the shop floor to the top floor with the PLC SCADA system, the MES, probably the most important centerpiece here, the manufacturing execution system, all the way up to the enterprise management solutions like the ERP system. And then this is coupled with a lot of smart manufacturing platforms and softwares. Plus a new layer I integrated is data-centric platforms, because this is getting more and more important. So on the right side of this slide, you find all these additional boxes and blocks that you can use, like product lifecycle management to deal with all the batteries you produce. I think very important for today, the QMS, the quality management systems, all connected to the laboratory information management you can get. Then in the second orange pillar, you see a more supply chain and warehousing solutions that are being employed to kind of orchestrate the material flow in the facility. The digital twins for the product, the production assets, or even the building. And then you need to kind of store it either in the edge of your network, can be on the premises of the gigafactory, or you move data to the cloud. So here we have kind of a convergence play between the classical hardware OT domain and the IT domain. And then it's always a question for the cell maker. What should we do on site? What do we need to put in the cloud? How quickly can we process data and where to store it? And this is why these data-centric platforms on the right are becoming more important. Obviously, cybersecurity. I think in Europe, we had one case where a security leak caused production to stop. So you don't want this to happen. Then basically a layer that allows you to analyze and visualize data, store them in lakes, warehouses, whichever is your preferred concept. Then, of course, AI, inevitable nowadays, to also include some functionalities from this. And if you want to then pass on data, for example, on your ESG enterprise platforms or the battery passport interfaces, you can have an additional data transfer layer on top of this all. So all these platforms interact with each other, which is not depicted here for the sake of simplicity, but just imagine that you need probably most of these solutions if you want to have a efficiently functional gigafactory that checks all the boxes. And some of the features could look like this. It's another very content-rich slide. I was already highlighting some of the quality-related cases in this case, but you have some functions that include just the shop floor management using the digital platforms to kind of orchestrate everything. So I would say like your MES is kind of the brain of your shop floor that really manages all the campaigns, the recipes, and executes the production, or gives the orders to execute that production. And then you have to manage the assets on the shop floor, which is your machines, keep up the uptime, reduce the downtime, and predict the maintenance if you can. Quality, closely related to the process steps and the product properties. Big topic will be featured in the last section of this content. And also the inventory management, where you check what's happening in the warehouse. Can we track and trace materials throughout the whole gigafactory, and what's happening with the supply chain? So you will find a lot of these things that need to be put together, and that can get quite complex given the zoo of solutions we're usually employing.
Excellent. So I'm interested in to dig in on a couple of these topics. If you could go to the previous slide where you show the full layout of all the systems. So really interesting, this topic of digital twins and the notion of using digital twins at kind of multiple levels of the physical process, the building, the process, the machine, the actual product itself. So I wonder if you could just go into a little bit more detail about what types of digital twins at sort of each of those levels is employed, at what stage, sort of like, I'm aware of use cases of digital twins in kind of ramping up and planning a production facility or commissioning, and then there's there's operational considerations as well. So I wonder if you could just give a little bit more overview of how digital twins are used in this process.
Sure. Maybe first the disclaimer that if we now talk of the digital twin, it's probably not what in traditional literature people would understand here, which is really bidirectional, completely soaked digital representation of these assets here. But it can be a digital model to begin with, or a digital shadow. And that's something that I think even in the planning phase, most cell makers now have on their technology radar they want to employ. And of course, they are facing the ramp up data gaps, so they don't know how to feed it with these live data yet, but they want to be ready for it. So that means once you start planning the facility, I think what most also start and scale ups did is get a BIM, a building information management system, that also gives you the visual clone of your facility, that you can walk through it, see where the piping is, see where the machines are going to be located. And if you were to put machines into it, that the doors would actually allow the equipment to be shipped into it. So these models are being employed before the production starts. And I think once the production goes live, I think every shop floor engineer is getting a bit nervous at this point that it works out like planned and intended. But then you should start receiving data from your machines that you can then feed into these models. And if the plan works out, you're live and you can learn from this alone. So I think it helps in the planning. This is usually done. Then in the ramp up, it's probably functional, but then I think there's so many problems happening through the ramp up that the question is, can you efficiently leverage the insights you generate through these digital models to actually help you troubleshoot or not? You need to call people to help you out with this. And I think the ultimate stage is that you would develop the digital twin of each and every product you're producing, not just of the battery cell, like the basically list of parts that you're producing, but that each of these battery cells that is coming out of the production and ending up in a vehicle, that it has a unique identifier, that the production data you gathered, especially information aging, are kind of put as a product passport next to the battery cell, and that you can hand this over to your client so they can benefit from these individual battery cell data. And this, if you can manage to put this into the vehicles later, that you know what's the history from the upstream materials through cell production, through the employment phase on the fields, if you have storages or EV applications. I think that's still a very futuristic case that, in my opinion, still needs to be demonstrated, because that requires a lot of working together between the supply chain partners and also, taking their guards down and being able to share this, because transparency is sometimes not the most appropriate way to share data.
Yeah, and I really like the thread a few years ago, we started using the word digital thread as well, in parallel to digital twins. And I think a lot of, what we've seen in the early days of digital twinning technology is people can create nice models, but it's essentially a garbage in, garbage out type of problem. So unless you get the right digital thread with real empirical data feeding into these models, you can create a model, but as soon as the real world comes, it, punches you in the face and everything goes out the door, and those models go out the door with it. So I think just having that digital thread throughout the factory is really one of those first pieces you have to make sure that you're set up to do. And yeah, I think the other thing, just like looking at this slide and seeing some of the questions from the audience, make sure to ask your questions in here. We are actively looking at them. It's a bit overwhelming looking at all these different solutions and different tools and how do you put them together. And the reality is, just going to a lot of these factories, most of these solutions, have been sold. They're not really implemented or barely doing very much at most of these factories. They're just sitting there. They are not well integrated. People don't know what data to get into the cloud, what data to feed in between the systems, what is the appropriate data to bring in. And so, yeah, a lot of the data just lives on the PLC level. It doesn't actually go much higher than that, or it doesn't get connected all the way up to the ERP or between the systems. And so that's where I think there is a huge need we're seeing in the market around really domain-specific solutions that help bridge and really glue all these things together and provide that level of insight. And that's, where I think where we're at Voltaic really trying to find that opportunity. There's a whole range of generic, ERPs, MESs, and others, but trying to bridge those together where you can get real battery insight across them rapidly is really the missing gap here.
Excellent. Yes, and speaking to an audience question about digital twins, it was along similar lines, but effectively they're employed at different levels for different reasons. Whether you're looking at a digital representation of a process or a digital representation of an individual cell. In our world, in our business, the idea of a cell level digital twin comes up a lot. As Tal mentioned, we like to talk about a digital thread, and it sounds like in this context, the digital twin of an individual battery cell is really just about the beginning of that digital thread that follows the battery throughout its life, as opposed to serving some vital, crucial operational function in the manufacturing environment itself. At least that's sort of how I interpreted it. I've got another question for Philip, and you've got the two the two hot topics between digital twins and AI. So I wonder if you could speak to what are some of this kind of aspirational use cases of AI and generative AI and these technological developments that over the last couple of years have kind of been sweeping through every sector. So from your viewpoint, what are some of the potential applications of Gen AI, let's say, in a battery production environment?
Yeah, that's a great question. We should do another webinar on this one because I think it's going to be extremely relevant topic for the future.
Sure.
I think the journey has started. I mean, the generative AI hype we've seen in the last month and years, lots of investment into solutions. More and more companies offering patchwork solutions, for example, in finding recipes for battery cell components, finding the sweet spot on the golden recipes. I'm a bit skeptical about this, knowing how complex it is to find the perfect golden recipe for a cell and, convincing a cell manufacturer to kind of use a solution and tune their secret recipe with this. But I think a lot of cases you can employ for process optimization and start with machine learning and simple AI first, like where can we really get the most out of the production data we get? I think AI helps us to identify the patterns that the human doesn't see, find the correlations between all these properties of the product and the processes that the operators and engineers are not able to see, and then basically help us to adjust this automatically. For example, if you go to the calendaring step after the electrodes have been coated, and there was a certain adjustment of the coating parameters, and you figured the coating got a bit too thick, and this information could be passed through automatically to your calendar. So it automatically adapts the width of the rolls and the gaps to kind of compensate for this production defect. I think this is something that artificial intelligence could do. I wouldn't say it's a generative AI use case in this case, but it helps. Generative AI, that's maybe a pretty boring case, but just the whole document management, writing reports, quality reporting, lab test results, instead of using template-based approaches, Gen AI can really help you to take a shortcut here. But there's still many more cases that will be explored. In fact, we're also internally working on assets like an operational digital twin. We fed with synthetic data and we're training it with an AI algorithm to kind of predict which battery cells could be bad ones, depending on quality use cases of the synthetic data. But this is still a long way to go. And, we're more looking in what does it take to actually employ these solutions? Like, where does it make sense? Also from an economic point of view. If you have a cool case, what does it help you to save you time, money, resources? And that's where you should be quite mindful about.
I want to pull, there's like a couple questions from the audience I want to combine. There's a question of where do you get started in the immense sea of digitization solutions? Where should companies start from our perspective? And then the other one is, how do you see the decision to build in-house versus buying externally playing out around the digital tool chain? I think they're very interdependent here. And, there's this really tough interdependency where it comes to, none of these tools, there's a lot of these tools, a lot of them are very generic, don't really don't have the right infrastructure to really help you get set up right away. Just as an example, if you bring in an MES, can it actually communicate with the PLCs coming out of Korea or China that you got for your equipment? There aren't those out-of-the-box integrations. The ERPs may not have any insight into what is actually scrap or not for your facility, and just all of those different, intermediary areas here are an open question. And so I think that leads a lot of people like, oh, there's no real solution, let's go build our own tool. But then again, you're looking at multi-year rollouts and build-outs because there's a lot of complexity and a lot of functionality built into these different components. And so I think it's leads to sort of this like analysis paralysis, or people going full bore to trying to build everything on their own, or the other way. And from my perspective, you need to start build that, system to start being able to look at data and learn from it, and build that feedback cycle into your process as soon as possible. Don't wait for the entire MES to be rolled out. Figure out how you can get some data off the SCADA to start making decisions quickly. Figuring out how to build that learning cycle around digital information into your organization sooner rather than later is really key. And then, we have not seen any of these homegrown solutions be successful on their own. Is just the reality of it. And so if it's just too much work, you don't have the staff, that is not your core business. But yeah, really interested in Philipp's take. You've been involved in a lot of these factories too. It's a big challenge. Where do you get started, and what do you do in-house versus externally?
Yeah, and I've seen it both, just buying the solutions off the shelf and developing it yourself. I think in both cases, the implementation effort and the troubleshooting need was underestimated greatly. Because years ago, when these solutions were needed in the planning phases of the factories, they were also still under development. I think especially in the Western industry, a lot of solutions weren't ripe yet. There were minimal viable products coming from other industries, let's say semiconductor, pharmaceuticals, mapped on the battery specifics, the discrete continuous processing mix and so on. But implementing them wasn't that trivial, because, the different types of data you suddenly deal with. And another interesting angle is usually a cell manufacturer is not building a single manufacturing plant, but has plans to build multiple of them, adding another layer of complexity. So what do we use in plant number one? At the point you build the second plant, you might have changed your plans because the software solutions got better, or you have changed your mind on a certain vendor maybe. And then you have suddenly legacy and locked-in solutions that you need to deal with. And this makes it even worse. And then you may reconsider, okay, we didn't make a great experience with the MES from a certain vendor. Then we quote someone, the MES is a mess. Then you might want to change that vendor, and this gives you extra effort again. You might consider even your own solution. But ultimately, people need to make quick decisions. So what's maybe resulting in the least budget overruns or costs in it, and what's actually functional at the end of the day, checking all the boxes for the requirements that you should have carefully written.
Yeah. And I particularly on this topic of like build versus buy, I really like the metaphor you used, Philip, to thinking about digital technologies as tools in your toolbox. That help you accomplish your goal of producing batteries of high quality, high yield, and low scrap. And if you think about somebody who sets about a do-it-yourself home improvement product, you start by making sure you have the right tools, and you go to the hardware store to buy the tools you need. You don't start by forging hammers and milling your own saws and hardware. You take the hardware from where it exists. Tal, do you have any more wrap-up comments? Kind of what we're seeing on the ground as far as what the actual maturity and penetration of some of these advanced digital technologies that everyone's talking about, and some folks are kind of dipping their toes in the pool.
Yeah, just looking at the questions here, there's a range of questions around Gen AI for root cause analysis, or deep transfer learning, and all these different approaches. And the reality is right now is there's not enough information because of the evolving technology, the range of root causes. A lot of these techniques are really theoretical in practice as far as the production line. I was talking to the CEO of a large battery company, and he says at current state, just basic regression and, and analytics, statistics goes actually a long way. And they're seeing a lot of the efforts around the extra overhead around the opaque AI models not really paying off quite yet. I think longer term, as we build more of the digital infrastructure, feed more data, have more information in there, we'll get there. But outside of discrete steps where I think it can be implemented well, the reality today is just focus on how you could learn today quickly. And, there's nothing wrong with statistics and regression and some of those good old techniques, that have worked well historically.
Excellent. So with that, Philip, I'd love to proceed, yes, to battery quality management.
I think the third and also very interesting part, I try to deal with this topic also coming from the product point of view. Maybe it's a bit theoretical, but just some considerations to bring us on the same page. So if you know batteries, and I think I built around 1,000 lithium oxygen batteries in the lab myself, and for some reason you just put your measuring device on it at 0 volt, and you're like, why? No one knows. It's just voodoo, and you have a spread of properties in batteries all the time. It might look like this, that you build a couple of batteries in the battery process. The smaller the spread of, for example, the capacity on the voltage curves here is. And what you want to define is basically a nominal capacity for your battery, and that's what you want to sell to your client. So, and now we try to, let's say, apply the good old statistical approach, the Six Sigma quality to it. So disclaimer, I'm not a Six Sigma expert. I just found this interesting to just give you some numbers. So if you are in a 40 gigawatt hour lithium ion battery cell plant, that means you produce roughly 60 million cells per year, 170,000 per day, or 119 per minute. So it will take you also roughly 1 week to produce 1 million of battery cells. If you want to now adhere to this quality standard, that the majority of the cells is within the Six Sigma range, so 3 standard deviations from this acceptable capacity where you cut off, that would mean that a scrap cell only occurs every 1 or 2 days, in theory. However, we do not see this in reality by far. So cell manufacturers then start grading by capacity, for example, say everything above a certain level, it's okay, we can sell it to a client, it's an A grade, that's what we promised. You have some minor flaws where you say, okay, let's take them for the in-house robots to power them. And then there's, of course, what everyone is most concerned about, the scrap cells, the no grades, the not okay battery cells, which can be declared this way for a variety of properties. And if you look at the actual scrap rates in the market, I think in the ramp up, it's not a shame to have up to 85% scrap. Can be for a variety of reasons. And of course, cell manufacturers wants to push this down as quickly as possible. And what I've heard is that in a highly optimized plant that has been operating for a while, you can maybe shoot for 2 to 5% of battery production scrap cells, which still means that the gigafactory of this size would produce thousands of batteries per day that you would need to discard and throw away. So for the industry, this is a massive cost-saving potential, a massive lever to kind of use the quality tools to help out in this situation, get the last 1-2% of yield increases in a highly optimized plant. And I think this is where then the digital technology comes in handy, which will be the late stage optimization. And I have some numbers for you where we assess the economic benefit soon. But basically, now grading is already done automatically. It's based on the production data we are getting. And a lot of this is actually being done, for example, in the formation system that gets you all the electrochemical data out of it. And then going the step further, this is where the real headache starts, applying advanced analytics to it, AI helping you out with this, but also managing this between all these platform puzzle pieces, your quality management system, the MES, the PLM, the digital models of this battery, and maybe your up to 3,000 inline quality or quality inspection points. That's the real challenge. And scrap is not scrap. So it's quite desirable that you detect it early on, the sooner the better, because as Tol said, it takes you some time to identify a scrap cell. And this is probably due to an extended aging step that you do at the end of the line. It's still roughly 2 weeks in industry. There's a lot of data-driven approaches promising to bring it down to, let's say, a couple of days, but no one is really willing to take this risk at the moment. But the sooner you would be able to predict that a battery cell is no grade or is going to be no grade, the more money you can save, the lower your scrap rate can be. And this is where the levers will be bigger. So basically a quality gate approach, and then going to the upstream part of the electrode production where you're still dealing with electrode faults and coils, and you find certain patterns or anomalies that you detected with your inline measurement techniques, where you say, okay, I know that this cell is likely going to not pass my quality test at the end of the line. Let me skip through all the other upcoming process steps, rework it, recycle it, or put it to the shredder. In-house and direct recycling might still be easy and possible at this point. But the more you go down the production lines, you're dealing with cell stacks that contain already a significant value share of your battery cells, but are still fairly dry and easy to process. But once you put the electrolyte in the system, in a conventional lithium-ion manufacturing flow, not talking solid state or dry coating or anything like this, but once you have the electrolyte added in the housing, this is getting more and more difficult to deal with this kind of cell, because then you also can't do a direct recycling anymore, for example. So basically then grading is important, and maybe you can still declare it as a C or B grade, but if you have any hints that this cell could lead to safety impairments, you don't want to ship this to a customer, and this will actually hurt you and your profitability. So good quality system early on might be able to prevent this. And I'm glad you also mentioned the digital thread. I think this term is becoming more and more standard. So that should be on each cell maker's agenda to basically establish this, achieve it from the upstream powders and components that you feed, in this case here, a powder handling and slurry mixing system, and follow these genealogy. No, I'm missing that word right now. Sorry for my bad English. You basically follow all these properties through the shop floor all the way to the finished good, and you know what happened with a certain batch on this day. Was there any events happening? Did any moisture content stand out in the titrations you did? What about the screw speed? And that's a lot of parameters as initially indicated. And this, if you have saved and stored it, you can track and trace everything in the facility. That sets the foundation for the quality protocols that we'll be running later. And we did some math on this. This was also taken from the white paper that we've published. The predictive quality use case is something that was very appealing, because in this model factory with like its 40 gigawatt hours per year, it could lead to savings of $25 million per year if you squeeze out a couple of more % of the yields by reducing the scrap. There is, of course, an investment required, especially the CapEx is quite high here. You need the camera systems, you need the sensors, you might need the computing resources maybe on your premises. It can also be the software license fees, the cloud fees, everything taken into the equation. We figured it's a return on investment if you do it, even for a rather optimized plant. We assumed a scrap rate baseline of 12% with a percentage improvement on top of this. And basically, if you were able to succeed in predicting the quality and lowering the scrap to this level, this would be a no-brainer to kind of go for such a use case. However, it still needs to be proven. I mean, the benefits are clear, and some of the enabler technologies cell makers are aware of, but you need to make it work and also demonstrate them to your management as a cell maker. Hey, we use this digital tool successfully to actually bring down the scrap. And I think this is what the Western, so the European and American industry is soon going to demonstrate, or they should, having some softwares or tools employed that actually lowered the scrap. I've heard cases or studies from the Asian market leaders who had in-house IT firms deploying such a solution, claiming that they brought down the scrap rate to a significant amount of, by a significant amount of percentage points. So this was quite impressive, and I hope that we can get similar success stories in the Western gigafactories too. And lastly, this is the last slide I have for you. It's more like the general recommendations if you're setting up a digital plant. Basically, circling to the architecture I've shown, you need to make it functional. I mean, don't underestimate the implementation. It should be ready when your plant starts producing. In terms of automation level, you also need to balance this, going digital and automatic, but not overdoing it. That's one of the key messages here. And also the same applies to the data management. If you just mindlessly collect data, you're just becoming data obese instead of data rich. It won't help you a thing. You just have to deal with more cost for dealing with this data. It's also not the ideal case. And then there's functionalities that you just must consider for compliance, for customer satisfaction. Traceability is basically also a no-brainer nowadays. And when it comes to DigiTwins, I think my recommendation here is be ready for the real deal. Basically set up the infrastructure that you can dock it to your existing solutions. And once you have enough data and you see the case for it coming with the volumes, go and show the benefits that comes with this. And overall, that's maybe the closing statement. You should know both the battery tech and the IT in this case. because these two departments also sometimes don't talk that much to each other in the Gigafactory project. And then basically having people moving between these two silos can also help to kind of get the project executed a bit more efficiently.
Wonderful. One question that came up in reviewing your content was this, you mentioned it very early on, and then again, this notion of battery manufacturing being a combination of continuous processes and discrete processes. Can you just go into a little bit more about what that means? I think people that are deeply immersed in battery manufacturing probably understand, but for the for the wider audience, what do we mean by continuous processes, discrete processes, and what are the specific quality challenges that arise by having to marry those two different types of processes?
Yeah, I think the easier one to explain is the discrete part of it, because you're dealing with individual parts that you can clearly assign a product number, a part number, and you can kind of hold it in your hand. It's quite simple to deal with, because these parts you can follow through the production shop floor one by one. And the continuous processing, which is basically the left third on the slide, up to the electrode production, this is where you're dealing with the continuous material flow of powders, liquids. So basically you're dealing with the slurry, conductive additives, binders, active materials all mixed together. In this case, extruded onto into the slurry and then coated with, let's say, a meters per minute parameter on an electrode film, a current collector film. And that's also something that kind of creates a rift in how you need to employ the solutions to it, because you need to bridge this. So the first part is the continuous one, which means you're then chasing a batch. For example, you have a ton of material in your mixer, you're doing a batch mix, and you need to then follow the material from this ton being transferred on various coils. And then you're now suddenly dealing with these discrete parts again, which need a whole different tracking solutions, because then you're dealing with QR codes, maybe laser markings. Will you do it on a coil level, or every meter on the coil, or even on every stack that you're cutting out? So basically you have differences in requirements for marking technologies and scanning. And also the IT must reflect this, because you can't employ these two traditional solutions. You need a mix of both. And this was actually one of the weak spots of years ago when SCADA and MES solutions were being sold, because this is new to the industry to have both of them, or it's a fairly niche industry that employs both of these cases. And some companies over the last decades have grown to be either focused on the continuous industries or the discrete manufacturing. And now you needed an industrial solution that manages both. So they actually had to, get their minimal viable product merged together in this case to be able to provide both insights.
Yes, and this flows very nicely into a question from the audience, and I wonder, Tal, if we could get your comments. The question was specifically about electrode level traceability, which is, effectively bridges that gap from the continuous to discrete. So, what have we seen implemented, and I guess, what have we seen as far as what companies have actually accomplished to date in this regard, and what are the concerns about the amount of data generated and our companies dealing with that?
I think we are seeing companies start to track all the way down to the electrodes. I think the challenges that Philipp highlighted around discretizing, especially if you look at continuous coats, how do you figure out which discrete part of that coat went into which battery? That area of really marking and understanding, which component went in where, especially if, this larger sheet that you may be cutting out parts that may have a scratch on it and scrap. And there's a range of companies that have helped really put together solutions there. We have a partner, PDF Solutions, who's really good at a lot of that intermediate traceability as well. But companies are starting to do that, and they are also, taking images of those coats and components. They're also taking images of welds and others. What's really needed here is, you can't store it all, you can't bring it all into one place, but there is a level of, essentially data hierarchy and, moving data to different tiers and, filtering certain data out. So if something does look good, it could actually be filtered out, but do keep track of some of that, those defects, and have that information in there. But really that kind of information, the information on defects and what caused that from the process parameters and different settings and materials inputs, ultimately having that information on what is a failure and what caused it is what's going to feed some of these more these AI models at the end of the day. But people are starting to track it. They are bringing in the data. They're getting smart about how that data is stored and which data does get persisted at what level. You don't need all of the raw data, but maybe just the couple data points off of it. But it's coming. People are putting together these technologies.
And Philip, sounded like you had some thoughts as well.
Yeah, I think it's also still under development from like a technology readiness point of view, and it's a maturity journey. So new cell makers, they don't know what do we need to track or where does it make sense. If you have a pilot line running and you get a feeling for where the problems are, whether it's upstream in your electrodes or rather in the formation part downstream, you know how many quality checks you want to do. But I think electrode level traceability is the thing. But then you have this continuous roll of a coil with maybe 1,000 meters of length or 5,000. How many markers do you put on this? Every 30 centimeters where you're gonna put the cut later for the electrode sheet or not? But there's interesting approaches that I've seen, for example, that you mark it and cut out the affected parts and then splice it back together. So that's a super interesting approach that basically allows you to kind of have this continuous traceability, maybe also based on defects you observed, that you realize where was this defect again, on which meter of the foil, and then you can trace this back. But yeah, every cell maker has a different spin on this.
Excellent. Well, I think that's a good place to wrap it up. I've really enjoyed this hour. It's been really engaging. I feel like, there were probably a dozen different topics that could comprise a future webinar, each on their own. So we'll look forward to scheduling a couple of those going forward. But in the meantime, thank you very much, Philip, for joining us and for sharing your thoughts with our audience and Voltaic webinar community. And we will look forward to keeping in touch. And to the audience, thank you very much for your thoughtful questions. And you can find all of us on LinkedIn. And of course, find out more information about all this stuff on our website as well. So thank you and have a great day, everybody.
Thank you.
Bye-bye. Thank you.